Hello, everybody. Welcome back. In this lesson, we will go over computations of limits of trigonometric functions. So when it comes to trigonometric functions, now when you recall trigonometric functions and trigonometry from pre-calculus or from algebraic viewpoint, you may recall many tools behind it, many formulas, many identities. However, when you consider trigonometric limit computations, you have only one particular tool available in the toolbox. In fact, it is a versatile tool that we can use for many different limiting computations. And let's try to understand exactly what that tool is going to be. Now, uh, this says This tells us about a very specific function, which is about sine theta divided by theta. You can have a different variable here. Theta is just a placeholder. So if you consider different, let's say, if you consider sine theta divided by theta, with the agreement of these three positions, let me use a different color. Look at this theta here, theta there, and theta right there. You need to have the same theta, same variable in all three locations. As far as you have this agreement, when theta goes to 0, sine theta divided by theta will result in 1. And this particular result is not algebraic. This is purely geometric and trigonometric. So the justification of this fact is also trigonometric and geometric, and we're not going to see the justification in our lesson. However, you need to understand the algebraic obstacle behind this computation. There is no way that you can bring this theta out because sine is a nonlinear function. Therefore, it has this electric fence around it. In other words, those parentheses are not allowing to bring any term out of it. So because of that, you cannot have this component theta interacted with anything outside of that. So that is the biggest obstacle that we may need to deal with in these computations. And to understand the scope of this, first of all, please note this down and have it as one single tool. And at the same time, there may be a certain level of trigonometry that we will need to work with trigonometric functions, but I promise you, it's not going to be millions of trigonometric formulas. So I will introduce them when I need them in applications. So as a first example, look at example number 1. Now, once you look at this particular scenario, now the only obstacle that you can recognize in this situation is having different constants in front of these components and uh, having a different variable, right? Having different variables in various positions. Now, to deal with this obstacle, this is the easy way that we can do, right? First of all, we need to understand the things that we can do and we cannot do. We cannot bring this 3 outside of this parenthesis, so function sine, because sine function is not a linear function. So what are we going to do with it? So step number 1. Now, since this is the very first example, I may give you some kind of intuition. But if you'd like to have a little bit of thought process for this particular problem, I recommend you to pause the video and think about it for a moment. And as usual, I'm not going to touch the limiting process. I will hold it for later. And then when I compute this, now look at this, sine 3x, this is untouchable component no matter what. However, what you can see here is 7x. You can separate that component. In other words, you can bring this one as like 1/7 factor in front of that fraction. And once you do that, the next step is now, uh, here you can recognize this constant. It's a constant multiple. Try to understand it is as an innocent constant that will not get involved with this entire computation because it doesn't have any variability. Now, the obstacle is yet the mismatch of these two components. Now there is a way around this. We can easily put factor 3 here. But when we do that, we are essentially changing the given function. Therefore, to avoid that change, I will multiply this term by 3. So in other words, multiplication and division by the same quantity is not going to change the function itself. And this is a common trick that we're going to have in many computations in calculus. And now the next step. Now we do have an agreement between these two arguments, these two terms. However, this term is unnecessary for this particular computation. Therefore, I will bring it to this particular constant fraction. And now let's write it in this form. X goes to 0. 3/7 is an innocent constant sitting in front. And then you have sine 3x divided by 3x. Now let's try to answer a couple of questions. First of all, the involvement of this constant. The constants are innocent in limit computations. So one thing that you can do is to bring it out right away because it's not getting involved. And then I do have sine, when x goes to 0, I do have sine 3x divided by 3x. Now look at this. I have 3x here, 3x there, but yet the obstacle is not having 3x here. But it is easy to fix. Look at this. When x goes to 0, what can you say about 3 times x? Where does that go? Does it have any other option? No, in fact, it yet goes to 0, but with a different speed. But yet it goes to 0. So now look at this component. We do have 3x going to 0, 3x there, 3x there. That will be aligned with exactly our tool, which is sine. Okay, so limit when theta goes to 0, sine theta divided by theta goes to 1. Now, in this scenario, the role of theta is now played by 3x as a common argument in this problem. So now when you compute this limit, this is what you get. The same constant sitting in front. I'm not going to change it. And this is none other than exact match with our tool. And that will give us the limiting value of 1. So the computation will yield 3/7. However, there was an completely incorrect way of working with this problem to sometimes incorrectly convince yourself towards an answer. For instance, if somebody says like, oh, why don't we bring this constant 3 out right away and then then to utilize the tool that we're talking about, and shouldn't that give us the answer? That will give you exactly the same answer, but the method is completely incorrect because that is going to violate the condition that sine is not being a linear function. So try to understand, sometimes you can get a correct answer exactly from perfectly incorrect method, and that perfectly incorrect method will result at a later point with a different catastrophe in a different computation. So make sure to do the computation in the proper way, the correct way. So let's look at another example. Example number 2. In this case, you do have sine 5x divided by sine 11x, where x goes to 0. But the problem is now here you do not have uh, anything to match with the tool. The tool is none other than theta goes to 0. Sine theta divided by theta equals 1. You need to have at least theta kind of a term in the denominator. Now, if you would like to take a moment and to think about it, please go ahead and do that. All right. Now, I hope you gave it a thought a little bit. And now Let's think about this. I need to introduce that kind of theta, kind of a denominator term to this problem. Now to do that, this is what I'm going to do. I will divide the top by x, and whatever I do, I'm going to do exactly to the denominator as well. In other words, now look at this. I'm going to divide both the numerator and the denominator by the same term x. Why do I do that? When I do it, I can introduce this term. At the same time, it's not going to change the function, because I can simply, I could do this, right? I can just cancel this. Flip and multiply the denominator, flip and multiply, and then x will get cancelled with x. So it's not going to change anything. But then why do we do it? We do it for one reason, because once we prepare that form, now we can answer individually to each component here just by employing the previous example. So in order to follow the same method, this is what I'm going to do to match with this constant 5. I'm going to introduce 5 here, and I'm going to introduce 5 up there too. So to match with the 11 here, I'm going to introduce 11 here, and then I'm going to introduce 11 out there. If you look at these two components, we can see those two are not getting involved with the computation. So I'm trying to make it, first of all, 5/11. So this is a constant that would move out of the limiting computation in the next step. And then I'm going to get sine 5x divided by 5x divided by sine 11x divided by 11x. Now this is perfect, because now you can think about when x goes to 0, you do have 5x goes to 0. You have the perfect match with this. In the meantime, when x goes to 0, you have 11x also going towards 0. That will give us exact combination for the next term. So that will yield the answer, just this term, 5/11, and then you have just 1 divided by 1, which will be trivial contribution to this problem. So it's going to be just 5/11. Now, if you proceed with the same idea, now one can see the same idea would work for different scenarios. Like for tan x, do we have a different tool for this scenario? No, if you do not have anything supplemental, nothing to worry. Just try to write what's given in the provided language. So when you consider sine 5x divided by cosine 5x, in other words, I write tangent in a different way, and I'm going to divide it by x. So in the next step, I can simply rearrange this term. It is sine 5x divided by x times 1 over cosine 5x. Now to answer for this one, we do know exactly the method. We would do the same trick that we followed before. We have an obstacle right here with the constant, mismatching constant. So I will multiply by 5, and I will place outside, and then I would say 5x goes to 0. Now look at this. This is an additional constant. That additional constant will appear in front, and then 5x goes to 0 will result sine 5x over 5x going to 1 times, and then this component, look at this, when x goes to 0 or 5x goes to 0, where does this go? This is a situation that you need to recall just a minor trigonometric fact. Cosine 0 is very innocent, because cosine 0, if you do not recall it, cosine 0 is none other than just 1. Sine 0 is 0, cosine 0 is 1. So cosine 0, once you plug in directly into this x equals 0, you're going to get cosine 0, which will result 1 over 1. So it's going to be 5 times 1 divided by 1. The answer is going to be just 5. You see, it is that simple. So another domain of these examples, example number 4. So in this scenario, now this is a completely different example where you have 1 minus cosine x. That simply means, where do we see sine? We need to have some kind of sine x over something, right? Sine x over x. But we do not have it. But that's exactly when you need to recall a trigonometric fact. You know cosine square plus sine square equals 1. This is the Pythagorean identity. And how can you utilize this one right here? When you consider sine squared x, on the other hand, that would be 1 minus cosine squared x. Now, once you look at this, one may say, oh yes, therefore we have sine x equals 1 minus cosine x. No, we do not have it for the situation of the linear terms. We do have it only with the squares. So how can you make this square here in this picture? It is very easy. If you recall the common trick that we used to get rid of square roots earlier, we can simply multiply the top and the bottom by the conjugate of the numerator. And when you multiply by the conjugate of the numerator, don't forget the original denominator stays right here. Don't change it. And then the conjugate computation will be meaningful only at the top. So that will give us, when x goes to 0, you're going to get 1 minus cosine squared x. After the simplification, it's going to be 1 square minus cosine square x, but 1 square turns out to be just 1. Now, this is what you're going to end up getting. And don't forget, don't neglect this component, the innocent component of the denominator, which results by the conjugate simplification. Now, at this point, the numerator has sine square. That's exactly this identity, right? The Pythagorean identity. So we have sine square. We do have this result for sine x over x, but we do not have it for sine square or something, right? So now when we have sine square, this is what we're going to do. We can break it into pieces. Sine x times sine x divided by this x square can be split into two pieces, x over x, and in fact we can make it separate like this. And then the third component is coming out of this innocent term, which is not getting involved with anything at all. Now when you consider this scenario, can you see you can provide a perfect answer? When x goes to 0, you have this component going to 1, this component going to 1, both are coming from the same tool, and then this component is heading towards a direct plug-in. When x goes to 0, it's going to be 1 over 1 plus cosine 0, where cosine 0 is going to be 1. So now 1 coming from this, and then the second one will give again another 1, and the third term will give you a 1/2. So when you multiply all of them together, you're going to get just 1/2. So now, these are a few meaningful dimensions of computations of trigonometric limits that you can think of. Now let me provide you a few bonus examples. If you'd like to challenge yourself a little bit, think about these problems. I'm not planning to provide you with any solutions at this point, but if you followed the method provided in the previous attempt, in the previous example, the same should work in this scenario. But there's a subtle difference in that scenario you need to figure out, but it's going to be even easier when you figure out that particular point. And the next problem is uh, a little bit of a different one, because for all of these situations we had x going to 0, and here I do have x going to pi over 4. The only component that I wanted to emphasize in this scenario is to show you that kind of a difference. I mean, the method that you're using even for this particular problem is exactly the same. So you need to utilize a little bit of trigonometry to transform the problem to the version of the tool that we are using. And I will leave it as a little bit of a challenge for you to think about. And with this, we conclude trigonometric limits, and you will find more interesting examples in uh, mathematized problem solving sessions. But beyond that, this summarizes pretty much like all different aspects of trigonometric limits that you should be familiar with. I'll see you in the next lesson.